Hi, good morning. Hi, guys.
Hi, good morning.
Hi.
Oh.
I promised you last week we are going to talk
Good
about.
morning.
Hi. We're going to talk about how to solve larger systems of linear equations today. Okay. No matter how many equations, no matter how many unknowns, the system. Mute your microphone, please. Karen, so mute your microphone, please. Yeah, the main thing we're going to do today is how to solve larger systems, no matter how many equations, no matter how many unknowns. Okay. But before that, we need to review some basics. The first thing I want to review is elementary row operations. 3 operations we can perform. The first one is to interchange 2 rows. The second one is you can multiply a row by a non-zero number. And the third one is you can add a non-zero multiple of one row to another. The second one in particular, you are not allowed to multiply a row by a zero. You have to multiply a row by a non-zero number. On Friday, we also defined row-reduced echelon form. A matrix is in row-reduced echelon form if all the 4 conditions are satisfied. For the people who did not show up for class on Friday, I want to mention we do have classes on Friday. It's mandatory. We had a lecture class on Friday. 4 conditions. Very shortly, we're going to review the 4 conditions. Okay. Row-reduced echelon form is what we meant by the simplest form. On Friday, we covered how to perform row operations to make any matrix in row-reduced echelon form. The whole procedure, the algorithm is called Gauss-Jordan elimination. The steps, we're going to review the steps today using some particular questions. For the people who did not show up for Friday's class, you need to take a picture of this screen, row-reduced echelon form. Okay. 4 conditions. If a matrix satisfies all the 4 conditions, then we say the matrix is in row-reduced echelon form, row-reduced echelon form, or reduced row echelon form. In any case, we call the matrix RREF. Also, for the people who did not show up for Friday's class, take a picture of this screen. This is the step procedures, my simplified procedures for making a matrix into RREF, how to perform row operations, how to choose the operations. Take a picture of that screen, please, for the people who did not show up for Friday's class. For this screen, so don't worry too much yet. That's the main thing we're going to talk about today. We'll cover that in more detail. But now let's start from the matrix, start from the linear system on the screen. On the screen, we have a pretty large system, a system of 3 linear equations in 4 unknowns, right? We are going to talk about that's a valid system. We are talking about how to solve a system like this. For any system, now let's recall we start from the augmented matrix. Now, I want you to write down the augmented matrix, please. So this is too simple. We'll do it together. Okay. The question is to ask you to solve the system. That's one of the questions on your handout. On your handout 1. Open your handout 1, you'll see the question. The question is to ask you to solve the system. A system of 3 linear equations in 4 unknowns. We start from the augmented matrix of the system. Each row determines each equation determines a row. Each variable determines a column. The first row is determined by that equation. The first equation, 2, 4, 6, 4, negative 2. The second row is determined by the second equation, the coefficients of the second equation, together with the constant term. I'm trying to review the terms, the names. Negative 1, negative 2, negative 2, and then the next number is 1, and then the constant term is 2. Right? I think I got everything right. And the last row is 2, 4, 8, 12, then 4. We use a vertical bar to separate the coefficients and the constant terms. The coefficients and the constants. We write a vertical bar, something like this. And then we are going to perform elementary row operations to put the matrix into RREF, into row reduced echelon form, or reduced row echelon form, however you say it, we say it RREF. I'm on that screen. The first thing we do is to create the leading one of row 1, to make leading one of row 1. By that we mean we want to do something, we want to perform an operation, elementary row operation, to make this location 1. Anybody want to tell me how to choose a simple operation to make this location 1?
Interchange by 2.
We don't have to do that. If we interchange row 1 and row 2, we have the next step we have to multiply a row by negative 1. I think it's simple. We just multiply the row by 1/2. We just multiply row 1 by 1/2. That's the second operation. 1/2 is a non-zero number. Okay. The operation we are going to perform is to multiply row 1 by 1/2, and the row 1 is changed. That's the notation for the operation of multiplying row 1 by 1/2. So we have a new matrix. The new matrix is simple, right? 1, 2. You just divide all the numbers in the first row by 2. I think you have 1, 2, 3, 2, negative 1. The next 2 rows are not changed. Okay, now I'm going to make some more comments. Yeah, probably I want to use a different screen. In many cases, we want to make leading 1 and avoid fractions. So now let's say if you have a matrix, say something like this, so maybe 3, 3, 2, 1, 1, 5, and then the second row is so maybe 2, 2, 1, 1, 1. The third row so maybe is 3, 2, 1, 1. In this case, how we want to perform an operation to make this location the first non-zero number in the first row 1. In many cases, we do not like fractions. Of course, it's possible to multiply row 1 by 1/3. That's one way to do it. But if you do that, you are going to make many fractions. Now, for instance, this number is going to be 2 over 3, 2/3, right? That number is going to be 1 over 3. Anybody want to tell me how to perform an operation without creating any fractions? I'm going to do the main question. When I do the main question, I'm going to make some comments. Anybody want to tell me how to perform an operation, elementary row operation, without creating any fractions?
Could you do row 1 times -3? Or plus the multiple of -3?
Yeah, probably you got it right. Okay, all you need to realize is 3 minus 2 is 1. You can add -1 multiple of row 2 to row 1. That's how you can get 1. What I meant is you can do something like this. I'm not going to write all the numbers, but by performing the elementary row operation is something like you multiply row 2 by -1, and then you add the multiple to row 1, and then row 1 is changed to that. So remember the notations of elementary row operations. Use the proper notations. Okay. So basically, the new row 1 is going to be 3 minus 2. At this location, it's going to be 3 minus 2, so which is 1, right? And then you have 1 in here. I believe you are going to have 0 here, and then you have 4 in here. And then you add -1 multiple of row 2 to row 1. You can make this location 1 without making too many fractions. Okay. I think the operation I was trying to write is R1. The new row 1 is changed to the old row 1 minus row 2. Okay. Do something like this. Again, in general, I want you to push the fractions as late as possible. In many cases, it's not possible to avoid fractions, but push the fractions as late as possible. So because when performing row operations, when you do this, you really do not like too many fractions. A little bit of comment on this. And also the location of leading one of row 1. I'm going to make a little bit of comment on that. Make the location of leading one of row 1 as far left as possible. As far left as possible. What I'm trying to say is if you have a matrix, now let's say something like this. Now let's say 0, 0, 1, 2, 3, and then 0, 1, 2, 3, 5, and then so maybe 0, 0, 1, 1, 2, 2. If you have a matrix, something like that, what would be the location of leading one of row 1 in the final form? After performing row operations, so there's no way to make this location 1. So because all the numbers in column 1 are zeros, right? And then this location is 0. Is it possible to make this location 1 by performing row operations?
No.
It's possible you interchange row 1 and row 2, then this location is going
Yeah,
to be
if
1.
we interchange, we
Yeah.
can, yeah.
I'm trying to say make the leading one of row 1 as far left as possible. So do not see a 1 in here. This is not the location of leading one of row 1 in the final form. In the final form, the leading one of row 1 has to be at this location. I gave you the simplified version of the step procedures while I'm making more comments. In the notes on the course manual, you have more detailed step procedures. Okay, I was trying to make some more comments. Okay, but the question we are doing now, the main question we are doing now, is simple. This one is going to be the leading one of row 1. In the whole procedure, the whole procedure is called the Gauss-Jordan elimination. In the whole procedure, this one is not going to be changed. Okay. We're done step 1. Now look at 2. Step 2, I mean, okay. In step 2, we are going to use leading one of row 1 to make all the numbers below that leading one zeros. That's the meaning. By that we mean we can use the circled leading one of row 1 to make these two locations zeros. We want to perform two. When making zeros, I told you on Friday, when making zeros, it's permissible to perform two operations in one step. I want to repeat, when making zeros, only when using a leading one to make zeros, you can perform two operations in one step. You can perform more than one operations in one step. Actually, you can perform two operations, three operations, more operations if there are more rows. Okay. In here, I'm going to tell you what are the operations we are going to perform, and then I will give you a little time to get me the new matrix. We are going to get a new matrix with two zeros at this location and that location in one step. Okay. We multiply row 1 by. Anybody want to tell me a multiple to make this location 0? So what multiple of row 1 add to row 2 can make this location 0? It's just one multiple, right? You multiply row 1 by 1, and then you add the multiple to row 2, and then the row 2 is changed to that. Right? The new row 2 is going to be the old row 2 plus row 1. We want this location to be 0. And then mute your microphone, please. Mute your microphone, please. Anybody want to tell me a multiple you need to make this location 0? What multiple of row 1 you want to add to row 3 to make this location 0?
-2.
Yeah, -2, -2. By that we mean we multiply row 1 by -2, and then we add the multiple to row 3, and then row 3 is changed. Of course, you have to change other numbers correspondingly. Our target is to make the two numbers below the leading one zeros by performing two operations. In many cases, we perform two operations. Number 3. Okay. Number 3 is to add a non-zero multiple of one row to another row. Right. Okay, now write the new matrix for me, please. I will give you a little time. I'm looking for the new matrix. After that, we'll compare the answers. Okay. I'm going to hide this screen. It's weird. I cannot write on the other screen. It's weird. I cannot write on the other screen. My pen cannot be moved to the other screen. Okay. Okay. In any case, I do not want you to copy. I want you to do it on your own. Okay. And then we compare answers. Anybody want to tell me the new second row?
0 0 1 1 1.
I think 1 2, is that right? 0 0 0 1 2.
No, sir. 3 minus 2 is equal to 1.
Okay. Did I do anything wrong? Probably I did something wrong. Yeah, I think you're right. You're right. 0, 0, 1, 1, 3, 1. Is that right?
That's what I got.
Sorry, I was looking at some other questions. My answer to some other questions. A different question, I guess. 1, 3, 1. Anybody want to tell me the new row in here? 0, 0, 2. 2.
8, 1. 8, 2, sorry, sir.
I think 2, 8, 6. Is that right? Can anybody confirm I got the right numbers?
That's what I got.
Okay, sure, thank you.
Yeah.
If you don't have this, we multiply this row by negative 2 and then add the multiple to here. So negative 2 times 3, you have 6. Negative 6. And then plus that, you have 2, and so on. Right? Okay, we'll move on. So we have made the two numbers below the leading one of row 1, 0. I'm going to circle all the leading ones. This number is not going to be changed in the whole procedure. Rather than the first round, and then we'll go back to repeat. We make leading one of row 2. This is the location of leading one of row 2. Again, make the leading one as far left as possible. Because all these 4 numbers are zeros, you cannot make any number at this location 1, right? This is the location of leading one. That's actually the leading one of row 2. And then the next thing we do is to use this leading one to make the number below that leading one 0. Okay. I hope I can fit everything on this screen. I believe you can see the multiple you need is negative 2, right? You multiply row 2 by negative 2, and then you add the multiple to row 3. Row 3 is changed. We perform that operation, use proper notations. And then we are going to get a new matrix. The first row is the same. I think 1, 2, 3, 2, negative 1. The second row is also the same. We want that location to be 0. That's what we got, right? Anybody want to confirm I got the numbers right? I think this one is too simple to all of you guys. Okay. So we got the leading one of row 2, and we made all the numbers below the leading one of row 2 zeros. And then we need the leading one of row 3, of course. Now look at the screen. This number now is not 1. Okay, we want this location to be 1. That's going to be the leading one of row 3. Now I'm going to circle all the leading ones of all the rows. These numbers are not going to be changed. We have to make this location 1. There's only one way to do it.
Minus R2.
We multiply row 3 by, so not minus R2. We have to multiply row 3 by 1/2. Right? We want to make this location 1. We multiply row 3 by 1/2. There's only one way to do it. So do not move all other rows to row 3 or other numbers that could be changed. So we have it's a little bit long to copy. Another comment when making leading ones, so please perform only one operation in a single step, or otherwise you could mess something up. You can only perform multiple operations in one step when making zeros below the leading ones or above leading ones. Okay. Still, I'm going to circle all the leading ones. You see, these numbers are not changed in the whole procedure. After getting all the leading ones and making the numbers below all the leading ones zeros, now we're going backward, right? Now look at here. We are done step 3. We have made all the leading ones of all the rows and made all the numbers below the leading ones zeros, right? And then we start from the last row. We use the leading one of the last row in step 4 to make all the numbers above the leading ones zeros. Eventually, we're going to have matrix in REF. Okay. The next thing we do is to use the leading one of row 3 to make these two locations zeros. We can perform two operations in one step in this case. Okay. We'll do the same thing. I will give you the operations, and then you write the new matrix. Try to write everything backward. Okay. To make this location 0, we need a multiple of -3. You think 1 times what number plus this 3 is equal to 0. The multiple is negative 3. By that we mean we multiply row 3 by a multiple of -3, and then we add the multiple to row 2. Backward, right? And then row 2 is changed. After performing the operation, you get a new row 2. And likewise, we get a new row 1 using that leading one. So because these three numbers are zeros, all other numbers are not going to be changed. Only the numbers above that leading one are going to be changed, are going to be zeros. The multiple you need, I believe, is a multiple of -2. By that we mean you multiply row 3 by a multiple of -2, and then you add the multiple to row 1, and the row 1 is changed. Use proper notation, please. This number is going to be 0. This number is going to be 0. I just want you to tell me the two numbers above this 2. So please, anybody want to tell me the two numbers at these two locations? So please.
-5 for the first one.
Okay, -5. The other number, I believe, is also -5. Is that right? We're almost done. I run out of space in here, but I will move the thing to the next screen. So maybe to here. We're going to get the last matrix. Okay. In one more step, we're going to have the final form. By the final form, I mean a matrix in row reduced echelon form or reduced row echelon form in RREF. Leading one of row 3 is here. Now all the numbers above that leading one are zeros. And then we use leading one of row 2 to make the number above this leading one 0. I think it's easy now. The multiple you need is -3. By that we mean you add -3 multiple of row 2 to row 1. You want this location to be 0. We multiply row 2 by -3, and then we add the multiple to row 1. Row 1 is changed. In one more step, we are going to get the final form to get the matrix in RREF. We need a new row 1. We wanted this number to be 0. Right? Anybody want to tell me the first number? We miss only one number. So please. Anybody?
-11.
-11 may not be right. Anybody else?
-8.
I think this number is 10. Is that right? Okay. I think 10 is right. You multiply this number by -3. By -3. -3 times do I add? Sorry, I was looking at the wrong line. You multiply this number by -3. -5 times -3 is -15, and then plus this number. I think 10 is right. Now, do we have a matrix in row reduced echelon form? For the people who did not show up for Friday's class, I'm going to review the 4 conditions. You look at your phone. Look at your phone. I told you to take a picture. On your phone, you have the 4 conditions. The first condition is if there is a row consisting of all zeros, it must be located at the bottom of the matrix. That condition does not apply. We do not have a row consisting of all zeros. The second condition is the first non-zero number of every row is 1. These ones are called leading ones. That's the leading one of row 1. That's the leading one of row 2. That's the leading one of row 3. The third condition is that the leading ones are in steps. That's what we meant by echelon. In steps. By that we mean the leading one of row 2 is to the right of leading one of row 1. The leading one of row 3 is to the right of leading one of row 2. That's what we meant by echelon form. And then the last condition, condition 4, requires that all other numbers in any column with a leading 1 are zeros. Thus leading one of row 1, 2 other numbers are zeros. Thus leading one of row 2, 2 other numbers are zeros. That's leading one of row 3, 2 other numbers are zeros. Before getting the solution, so please do make sure all the 4 conditions are satisfied. By that we mean verify the last matrix is indeed a matrix in RREF, row reduced echelon form. After getting the final form, we are ready to get the solution to the system. Actually, this time you see a matrix that is a little bit weird. You remember in the first class I told you there are 3 cases to any system. A system can have no solutions. A system can have one and only one solution. We say a unique solution. A system can also have many solutions, infinitely many solutions. Now, after getting the final form, now the new stuff for today. We start the new thing for today. How to get the solution to the matrix. Now for all of you guys, I want you to take a picture of this screen. Take a picture of this screen. I will make some comments on how to get the solution to any system. You do not need to copy. I want you to take a picture. This screen is in the course menu. You do not have to copy. Take a picture, so you have it on your phone when I talk about how to get the solution. Okay. You got the picture? I think that's it. We'll go back to that screen soon. But now I'm going to talk about all the cases. The first case is in what case a system has no solutions. Now you imagine you start from the augmented matrix and you perform row operations to get the final form to make the matrix into REF. Augmented. You perform a list of operations, a series of operations to make the final form. Now let's imagine the final form is something like this. I will make up a matrix. If the final form is something like this, so now let's say 1 0 0 0 2, so maybe 0 0 0 1 1 2, so maybe something like this. 0 0 0 0 0. So maybe something like this, 1 0 0. This is the case. Is the matrix in row reduced echelon form? Is the matrix in REF? You can check all the 4 conditions. The matrix is indeed in REF. The matrix is indeed in row reduced echelon form. Check all the 4 conditions. If the final form is something like that, anybody want to write something down? Write something down and tell me what is. Now let's recall each row determines an equation. Each column to the left of the bar determines a variable, an unknown. Anybody want to tell me the equation determined by the last row? What is the equation determined by the last row? 0 equals 1, which is never true, right? Which is never true. This is the case the system has no solutions. Now look at your phone. This is the case the system has no solutions. On your phone, you look at the condition under which the system has no solutions. If there's a leading 1 to the right of the bar, if there's a leading 1 of some row to the right of the vertical bar, then the system has no solutions. So because the last row corresponds to an equation 0 equals 1, this is never true. Actually, in many cases, if you... Okay, I'm going to make more comments on that later. But you imagine you get the final form. In the final form, if there's a leading 1 to the right of the bar, then all the numbers before that leading one has to be zeros, and then that's the case. The system has no solutions. This is the case. The system has no solutions. Now the next case, under what condition the system has a unique solution? I'm going to show you a particular matrix. Now let's imagine the final form is something like this. Again, you start from the augmented matrix of a new system, a different one. Okay, and then you perform elementary row operations. If the final form is something like this, so now let's say I do not want to make the thing too complicated. Yeah, probably you'll see something like that on your assignment. Now let's say something like this. Let's say 0. I do not want to start with 0. Let's say 1 0 0 0 1 0, and then 0 0 1. So maybe 1 2 3. Now let's imagine there's a new row. The system has 4 equations. The last row, now let's say something like this: 0 0 0 0. This is the case. The system has a unique solution. Now you look at the screen of your phone. How do you check the system has a unique solution? You check the columns to the left of the bar. Now listen to me carefully. We are talking about the new thing. You check the columns to the left of the bar. If every column has a leading 1, then the system has a unique solution. If every column to the left of the bar has a leading 1, and there are no leading ones to the right of the bar. Sorry, I forgot to say that. I want to repeat. If every column to the left of the bar has a leading 1, and no leading ones to the right of the bar, this is the case. The system has a unique solution, has one and only one solution. By unique, I mean there's only one set of the values of the unknowns satisfying all the equations in the system. Okay, I will make more comments. You check the first column. Does the first column has a leading 1? The first column has a leading 1 of row 1, right? And then you check the second column. Does the second column has a leading 1? The second column has leading 1 of row 2. And then the third column has leading 1 of row 3. Every column to the left of the bar has a leading 1. And no leading ones to the right of the bar. You have a 1 in here, so, but that's not a leading 1, right? If this is the case, the system has a unique solution. If the system has a unique solution, we are able to get the unique solution. Anybody want to tell me the unique solution in this case? Now let's use x, y, and z for the unknowns, for the variables. It's the same thing. So what's the value of x? What's the value of y? What's the value of z?
1 2 3.
1 2 3. And each row determines the equation. The first row determines the equation x equals 1. The second row determines the equation y equals 2, z equals 3, and so on. Okay. This one is simple. 2. The first 2 cases are simple. The first 2 cases are the 2 cases the system can have no solutions. The system can have a unique solution. We do not say we have 3 solutions. A set of values of x, y, and z is one solution. The system has one and only one solution. We say a unique solution. Okay, now take a look at the matrix we just did. The final form we just got for the system, for the main question we're talking about today. Is this case 1? Is this the case the system has no solutions? It's not case 1. No leading ones to the right of the bar, right? Is this case 2? By that I mean, is this a case every column to the left of the bar has a leading one? Tell me a number which column does not have a leading one. Which column does not contain leading one? Column 2. Column 2 does not have a leading one. Column 2 does not have leading one. So this is not case 1. So because no leading ones to the right of the bar, this is not case 2. Because it's not the case the system has a unique solution. So because there's a column without leading one, it has to be the case. Altogether, we have 3 cases. No solutions. A system can have no solutions. A system can have a unique solution. A system can have many solutions, infinitely many solutions. This has to be the case. The system has infinitely many solutions. Now let me summarize. Under what case the system has many solutions? First of all, there are no leading ones to the right of the bar in the final form. In any case, you have to get the final form first. There are no leading ones to the right of the bar in the final form. The other condition is there is at least one column to the left of the bar has no leading ones. In this case, column 2 has no leading one. Okay. Originally, we wanted to solve the linear system. Now you can say the system has many solutions. The system has actually more precisely we say infinitely many solutions. Infinitely many solutions. We are not done yet. Still, you said infinitely many solutions. A further question is, what are the solutions? Now we are going to have a way to represent all the solutions if a system has infinitely many solutions. In the future, I just say many solutions. The way to get the many solutions is we have something called the general solution. The general solution. We are going to use a representation of the general solution to represent many solutions. Okay. Still look at your screen. Your phone screen. It's on the phone screen. Now look at the phone screen. I'm going to tell you how to get the general solution. The general solution represents many solutions. How about we just talk about how to get it? Later on, I'm going to make more comments and telling you why the general solution represents many solutions. Now listen to me carefully, okay? Now we're talking about the general solution to the system, to the given system. It represents many solutions. Okay. I want to repeat. Each row determines an equation. Each column determines a variable. I said that many times, but now we're going to use it here. And but I think you just told me column 2 is a column without leading one. Column 2 corresponds to the unknown of x2. So that makes sense? The first equation is going to be x1 plus 2x2. Each column determines an unknown, right? To get the general solution, the first thing you do is to identify a column or all the columns without leading ones. In this case, column 2 is a column without leading 1. And the column 2 corresponds to the unknown of x2. Okay? And in the general solution, you set x2 to be a parameter. We're going to use the notations like R, S, or T to denote the parameters. At this point, you just remember how to get the general solution first, and then I'm going to make more comments. But by parameter, we mean x2 can take any value, can take any arbitrary value. A parameter is a notation, a variable that can take any numbers. In this case, any real numbers. We set x2 to be a parameter R. In this case, for this one, we have only one column without leading 1. So in the general solution, we have only one parameter. And then our next job is to write all other unknowns in terms of the parameter R. I want to repeat. First of all, you identify the columns without leading ones, and then you set the corresponding unknowns as parameters. You set the corresponding unknowns to be the parameters, I meant. The next thing you do is to write all other unknowns in terms of the parameters. Anybody want to tell me x4? I think the system has 4 unknowns, right? Anybody want to tell me x4? x4, you have no other choices. Now look at the last row. The last row determines an equation. x4 is... Anybody want to tell me the value of x4? Harjit, I think you told me 2 already. I think the last row determines the equation x4 equals 2, right? x4, you have no other choices. Has to be 2. Anybody want to tell me x3? x3, please. So write something down, please. Write something in the chat. x3, please. So please, I just want to make sure you are following me. Okay. Writing down x3. Look at the second row. The second row determines the equation x3 equals -5, which is easy. Okay, good. All of you guys got it right. And then the problem is the only problem is how to write x1 in terms of the parameter R. That's the scratch paper or your brain. Now, to represent x1 in terms of the parameter R, we are going to use the first row. The first row determines an equation. Write that equation first. I'm telling you the longer way first. Okay. The first row determines the equation 1 times x1 and then plus 2x2. You do not have to write the terms involving zero coefficients, I mean. Okay. The first row determines the equation x1 plus 2x2 equals 0. Equals 10, I mean. Sorry. Equals 10. Now x2 is R. You replace x2 with R. You have x1 plus R equals 10. Now that's the equation you need to use to represent x1 in terms of the parameters, or the parameter in this case. So x1 in terms of parameters represent x1 in terms of R. I believe you have 10 minus R, is that right? You solve that equation for x1. All of you guys can do that. That will give you the representation of x1. x1 is 10 minus r. I think you're right. Sorry. x1 plus 2x2 is equal to 10. Sorry about that. I think Harvey just told me I did something wrong. x1 plus 2r is equal to 10. x1 is equal to 10 minus 2r. That's right. Okay. So x1 in terms of r is 10 minus 2r. Sorry about that. And I want you to write something like you have to tell me the meaning of r. In the general solution, I want you to write r as a parameter. Okay, that is the general solution. I just told you how to get the general solution, and I told you the meaning of r is a parameter. Now I'm going to make more comments and telling you why the general solution represents many solutions. I told you r is a parameter, meaning r can take any number. Now listen to me carefully. I'm talking about a key thing. Why the general solution represents many solutions. Many solutions, I mean. R is a parameter. It means r can take any number. R can take 0, r can take 1, r can take pi, r can take e. For the people who take calculus, if you haven't done the calculus, it doesn't matter. Okay, you just imagine r can take 1.1, r can take 2.3, r can take any number. Now, does it make sense? Each value of r determines a particular solution to the system. Now, let's say r value of 0. If I set r value to be 0, that's not part of the solution. If I just want you to solve the system, but I still want to write this. R value of 0 so determines the solution of what? R value of 0 determines a particular solution. x1 equals 10, x2 equals 0, right? Because r value is 0, and x3 you have no other choices. It's -5, and x4 you have 2. Again, r is called a parameter. It means r can take any real number. Each r value determines a particular solution. R can have many choices, right? You have many choices of the values of r. That's why the general solution represents many solutions. Now let's get another particular solution. Okay, if I take r value of 1, we can have another particular solution. The particular solution determined by the parameter r value of 1 is x equals, anybody want to tell me this number? 10 minus 2 to 1. 2 times 1, I believe is 8, right? And that's x1. And x2 you have 1. x2 is r. x3 and x4 you have no other choices. x3 equals -5, and x4 you also have, and x4 you have 2, right? That's another solution. Now we have two different solutions. That's a solution determined by r value of 0. That's a solution determined by r value of 1. You have many choices of r. That means you have many solutions. So the general solution represents infinitely many solutions. That's the point. I think we have time to at least one more question. In the nature, we're going to do a larger system, an even larger system. So any questions so far? Anybody has any questions for the general solution? Last time we learned how to perform row reductions to make a matrix REF. This time the main thing is after getting the REF, how to determine if the system has a solution, and how many solutions, how to get the many solutions, how to get the solutions. Any questions so far? Okay, now we are going to if you don't have any questions, we're going to do an even larger system. That's another system on the handout. Okay. For this one, I want you to do most part yourself. Write the augmented matrix. The question is still ask you to solve the system. Now that we have a pretty large system, we have a system with 3 equations and 5 unknowns. This system is larger than the other one. We're going to practice many things. We're going to practice how to choose elementary row operations. By that we mean how to do the algorithm of Gauss-Jordan elimination, and so on. Okay. Now the solution, we start from the augmented matrix. So please, I want you to try most part yourself. There's something wrong already. If you look at the course manual, I believe this one is on the course manual, but I'm using slightly different way from what I told before. I told you last time, I think. The circle is the leading one of row 1. You do not have to do anything to make leading one of row 1. Now you can go ahead to use leading one of row 1 to make these 2 locations zeros. I think the operations we are going to perform is to multiply row 1 by -2, and then we add the multiple to row 2, and row 2 is changed. We multiply row 1 by 1 and add the multiple to row 3. Row 3 is changed. We said over and over again how to choose the multiples. I think at this point you should be able to do it. I want to repeat, when making leading ones, it's permissible to perform 2 operations in one step. You want these 2 locations to be zeros. I'm looking for other numbers. And when I confirm I have the matrix right. Earlier I did not want you to copy. You wanted you to try, and then we compare the answers. That's what you got? Thank you. Okay, after we get this, and then we make leading one of row 2, right? We made our target was to make all the numbers below the leading one of row 1 zeros, and then accidentally we created many zeros. The circled leading one of row 1 is not going to be changed anymore, no matter what operations you perform. If you see that number is changed, then you did not follow my algorithm. Actually, the algorithm is the fastest way to get you to RIF. You can perform any operations you want. I told you last time the final form is unique. By that we mean different people can perform different operations, but the final form is going to be the same. Anybody want to tell me the location of leading one of row 2? So tell me the column. Leading one of row 2 is going to be in which column? We want the leading one of row 2 to be at this location. Yeah, that's right. Column 5, column 4 actually. It should be column 4. 1, 2, 3, 4. So because you can bring this number up to make this location a non-zero number, right? You meant 4, I guess. That's what I meant, to make the leading one of any row as far left as possible. When performing row operations, make the leading ones of any row as far left as possible. Okay. The next thing we do is to interchange row 2 and row 3. We want this location to be a non-zero number first. In any case, I know it's simple. Do not perform 2 operations in one step. When making leading ones, you only perform more than one operation in one step when making zeros. By that I mean, in next step I want to interchange row 2 and row 3. That's what I meant. Perform only one operation in one step when making leading ones of any row. Now I want to make leading. We are ready to get the leading one of row 2. It can be achieved by multiplying row 2 by 1/2. I believe all of you guys see that. It should be simple. Right. Okay, we got the leading ones of all the rows, and we made all the numbers below the leading ones zeros. I circled 3 leading ones of the 3 rows. And then we start from the last row to make other numbers zeros, to make the numbers above the leading ones zeros. I'm not sure I have enough space on this screen or not, but probably it's easier if I move on to the next slide. I did not copy the bracket. That's the last matrix. I did not copy 1 in here. I believe I had 1. Okay, it's already leading one of row 3. Now we move backward. We use all the leading ones to make all the numbers above the leading ones zeros. Okay. To do that, you add negative 2 multiples of row 3 to row 2 to make this location 0. You add negative 1 multiple of row 3 to row 1 to make this location 0. Negative 1 multiple of row 3, you just write as negative row 3 and add the multiple to row 1. Row 1 is turned to that. Right? Eventually, we're going to have the final form. No, so not quite yet. Write this one backward. Do I have this right? I think I have this row right. Okay. Now we use the leading one of the last row to make all the numbers above the leading one zeros. I think we have more than enough time to finish that. In one more step, we're done. Now we're going to use leading one of row 2 to make this location 0, right? By adding negative 3 multiples of row 2. Eventually, we have the final form. I think the final form is Anybody has a different matrix? Anybody has a different final form? That's the final form. That is the matrix in RIEF in row reduced echelon form. Still, I want to circle the leading ones. Okay, now I want you to write something on the chat. Listen to my questions. How many solutions does the system have? Write something on the chat, please. Tell me how many solutions does the system have? No solutions, unique solution, or many solutions? Just write something in the chat, please. Yeah, many solutions, infinitely many solutions. Okay, and then many solutions, you have to choose parameters. You have to choose parameters. How many parameters do we have? What are the parameters? You write something like, so just tell me how many parameters first. two parameters, and what were two parameters? I think two parameters are right. To get how many parameters, you tell me. You identify the columns without leading ones. Column 2 is a column without leading one. Column 3 is a column without leading one. Correspondingly, I think Ben wrote it right. You set x2 to be a parameter. You set x3 to be a parameter. No other parameters. x1 is not a parameter because the first column is a leading one column. x4 is not a parameter because leading one of row 2 is in column 4, right? So we have two parameters. So you set x2 to be a parameter. You set x3 to be a parameter. Now I want you to, so please, now I want you to practice to get the general solution to the system. Get me the general solution to the system, please. Get me the general solution to the system, please. If I want you to solve the system, you have to answer the system has infinitely many solutions. I want you to get me the general solution. Do not copy from me. I want you to try. The general solution is going to be something like this. Your main thing is to get x1. I think Ben told me to set x2 to be a parameter. So how about we use R and S for the parameter? x3 is a parameter, right? How about we use S for the other parameter? So do not use different parameters for different unknowns. And then you get x1, x4, and x5. Yeah. Actually, for x1, I forgot to mention earlier. It's I really want you to do it by looking at the first row. If you are confused, you do it as what I did. You recover the equation from row 1, and then you set x2, x3 to be the parameter. But it's not hard to just do that. To just look at the first row and get x1. x4 you have no other choices. x5 you have no other choices. The problem is how to get x1. Okay. Again, when you are confused, get the equation determined by row 1, and then you will know what's going on. Okay. x1 equals, I think all of you guys who wrote it are right. Karen got it right. Everybody got it right, I think. x1 is equal to 3. Not 3. I think minus 2r and then plus s, is that right? Alright. So do not forget to mention, in this case, r and s are parameters. One additional question. The question is going to be on midterm. Yeah, probably I'm going to add a question to new assignment. After getting the general solution, if I want you to get two particular solutions, the question is designed to convince you the general solution indeed represents many solutions. If I want you to get two particular solutions, now please, I want you to get two particular solutions. Now let's recall each value, in this case values of the parameter, determines a particular solution. You just set a particular value of r, a particular value of s. So how about you just tell me the particular solution determined by r value of 0 and s value of 0. I don't have the space to write the full sentence, but I want you to get the general solution, the particular solution determined by the parameter values of r 0 and s value of 0. So just tell me the numbers in order, please. If r value is 0, s value is 0, then the particular solutions we are going to get is x1 equals, I'm looking for a value of x1 equals 3, I think, right? x2 equals 0, x3 equals 0, x4, x5, you have other choices. Sorry, I have space in here, but x4 value is 91, you have no other choices. And x5 value is 2, right? Yeah, I like that. 300 -1 2. 300 -1 2. Okay, that's one particular solution. If I'm looking for another particular solution. You have to choose different values of r and s. So how about we get another solution for r value of 1 s 1? So get me another solution, please. If r value is 1, s value is 1, please. So just tell me I hope it's not too messy when I'm saying it. I guess you know what I mean. So there are some questions to get the solution. Parameter values on your own. Okay, and then you get particular solutions. 2, 1, -1, 2.
Sir, when R and S, are we allowed to go like 1 and 3?
It's okay. It's still a different solution. As long as one of the numbers in as long as one of the unknown values is different, then it's a different solution. Okay, I think x 1 2, x2 1, x3 1, I guess. I did not check. I think I trust you on this. I think the x4 is equal to 91, x5 is equal to 2. That's the particular solution determined by parameter r value of 1 and s value of 1. Okay, now you can imagine you are ready to solve any system now. No matter how many equations, no matter how many unknowns, you are ready to solve any system. You just get the augmented matrix and perform row reductions. After you get the final form, there are only 3 cases. Right? You can determine if the system has a unique solution, no solutions, or many solutions. If you have many solutions, then it's easy to write many solutions. Okay, so that's all for today, and thank you. I guess many of you guys have another class. See you guys on Wednesday.
Bye, sir.
Bye. Thank you.